Kristen McQuinn. I'm a research scientist at the McDonald Observatory here at UT Austin. And I'm going to tell you about dwarf galaxies and how we use them as windows into the history of our universe. And dwarf galaxies are these really small, low-mass galaxies. But before I tell you about those, I'm going to take a step back and just talk about galaxies in general. So galaxies is this collection of stars and gas and dust and black holes and dark matter that are all gravitationally bound into what I like to think of as like an ecosystem. And we of course are inside of our own galaxy, the Milky Way, but there are billions and billions, I couldn't help but say that, of galaxies in our universe. This is one of my favorite images. This is from the Hubble Space Telescope. It is the Ultra Deep Field. And the Hubble Space Telescope, if you take a grain of sand and you will hold it out at your arm's length, this is the field of view that Hubble sees in the sky. It is that small. And astronomers took Hubble and pointed it at what we thought was a fairly blank patch of sky for a really, really long time. And this is the image that comes out of that exposure. Almost every single thing you see in this picture is a galaxy. And so you have things here that look like a spiral galaxy. These are fairly nearby. You have other ones that look like elliptical shape, these red ones here. But every single point of light you see in this, almost every single point is a galaxy. And so even the ones that look just barely bigger than a pixel are galaxies that are on the other side of our universe, that just when the universe was first forming galaxies and stars, these things started to emitting light, and it's taken 13.5 billion years for us to receive it at our telescopes. And there is this huge diversity of galaxies out there. Some of the ones that are most popular that we see in the media are things like spiral galaxies. This is the Pinwheel Galaxy, M101, and you have a spiral bulge as really one of the prettiest ones we have in the nearby universe. And in the center, there's a spiral bulge here filled with stars, and in the center of that, there's a supermassive black hole. There are these spiral arms that come out from the galaxy, and all the little points you see here in blue are individual stars. But then you can also see these darker kind of reddish-brown features in here, and these are lanes of molecular gas and dust. So the gas and dust is what fuels star formation in a galaxy. So when you see something like this, so it's got lots of material to make new stars, this is a really active, ongoing, star formation galaxy. We also have things that are elliptical galaxies. This is a really different type of system. It looks more like a football. There's not a lot of gas and dust that you can see in this image, so there's not a lot of ongoing star formation. It's mostly older stars that make up this galaxy, and it's a little bit farther away, so rather than being able to pick out individual stars, the stars are sort of blended together in this picture to make a sort of a smooth distribution of light. And then there is another one in the background here you can see in the image. But then there's other things that are kind of peculiar. This is the Sombrero Galaxy, M104, and it's got a little bit of both in it. You've got a disk of gas and dust in the middle here, and potentially you can think of if you were to stand up and kind of look back on the galaxy from like the top of it, it may actually look like a spiral galaxy. We don't really know. But you can see that it's embedded inside this sort of football-shaped distribution of old stars. So this is kind of a quandary for us. We don't really know what made the Sombrero Galaxy, why it looks the way it does. But it's fairly nearby and pretty interesting to study. In fact, I just measured the distance to this galaxy fairly recently. Despite its popularity in the media, we'd never actually had a circular distance to this galaxy. But we're going to talk about dwarf galaxies. So these look really different. This is a dwarf galaxy here, and it doesn't look like a spiral, and it doesn't look like an elliptical football. These are blobby, otherwise known as irregular galaxies. And this one is actually undergoing a burst of star formation, so it's kind of lit up like a Christmas tree. And if you look really carefully in this image, you might see, if you're maybe not so sure you can see in the back, but down here there is another feature in the picture here. This is an even smaller dwarf galaxy that is being pulled apart by the tidal forces of its more massive cousin. And this galaxy got too close, and it stretched out into this tidal stellar stream of material. And this is orbiting around the other galaxy, and we do believe at some point it will merge in to this larger dwarf. And while this galaxy is too small to create those same sort of features in the more massive dwarf, we do think that this tidal interaction from this little guy is what's causing this burst of star formation in the more massive dwarf galaxy. Okay. There are lots of dwarf galaxies in the universe. In fact, they're the most numerous type of galaxy there are. And in fact, around our Milky Way, we have a whole system of dwarf satellite galaxies. So in this picture here, this is the Milky Way, and all the little points around it are small dwarf galaxies that surround us. So much like our own moon is a satellite of our planet, these dwarf galaxies are satellites of our own larger spiral galaxy. And over here is our kind of our twin galaxy, Andromeda, and Andromeda has its own system of dwarf galaxies as well. And these are gravitationally bound too into what we call the local group. And so we are not just on an island universe in our own galaxy, but it's surrounded by our little dwarf friends, galaxies, and in fact, connected to Andromeda in a gravitationally bound group of galaxies, the local group. And in fact, we are discovering more dwarf galaxies in our own neighborhood every day. So when I first started in astronomy, there were a few dozen of our dwarf galaxy neighbors, and I thought that was sort of it. They're close by. We think we found them all already. But with new observational techniques, new instruments, and new analysis techniques, we're actually finding galaxies in our own backyard that are smaller and fainter than we ever thought possible. Okay. So I told you that I think of galaxies as ecosystems. You can think of it as like a forest, right? In a forest, you've got trees, soil, bacteria, fungi, animals, birds, a whole bunch of stuff. And the forests are geographically bounded, and they're also sometimes bounded by climate. Well, galaxies are ecosystems that are made up of a whole bunch of different constituent parts: gas, stars, dust, black holes, etc. But they're not bound by geography or climate. They're bound by gravity. And these ecosystems can also interact with other ones, as I showed you in the dwarf galaxy. But disentangling the history of something that looks like this is really complicated. In fact, I think of a galaxy like the Sombrero as a little bit like Singapore. And Singapore has a very complicated history. And you can imagine if you took a picture of Singapore and tried to back out the history of this unique location, it'd be kind of hard. You've got multiple languages spoken. You've got multiple cultures that have come together. You have, a complex high-rise along with really smaller, older, modest buildings. You have a very active port of things coming and going. And this is to say, it's extremely complicated. Well, studying dwarf galaxies simplifies things quite a bit. This is a local dwarf galaxy named DDO 165. And the blue points here you see are all the individual stars. The pinky purple regions are young star-forming areas. So this is where we have very, very young and massive stars being formed. And you can also see in this picture from Hubble Space Telescope, there's a bunch of background galaxies as well in this image. But this is a lot simpler to understand than the Sombrero Galaxy. And in fact, dwarf galaxies can even get smaller. So this is one of the smallest gas-forming dwarf galaxies that we've ever found. It's Leo P, and this is an image I took with the Hubble Space Telescope not too long ago. The galaxy itself are these blue points in the middle. And you've got, the field is rich with all these background galaxies. There are a bunch of foreground stars here you can see, but the galaxy itself is right here. And it's got one young star-forming region right in the center. So Leo P, to give you some perspective, here's M101, or the Pinwheel Galaxy again. This is the size of Leo P. So the entire galaxy would fit in one of these star-forming regions in this massive spiral galaxy. And so if the Sombrero is like Singapore, I think Leo P is a little bit more like Galapagos Islands. So it's isolated, you've eliminated all these other factors, and you're trying to understand the evolutionary history of something that's much simpler. Okay, so what do we use these galaxies for? Well, they really are a window into the past. You can look at the entire history of a galaxy, which includes understanding how many stars have formed in the galaxy and when. You can understand how the galaxy as an ecosystem evolved over time. But you can also try to connect what you learn about a galaxy to what was happening in the universe at different epochs of time. So these really are sort of time capsules to the past. And in particular, one of the interesting areas of study is the very early universe, when it was very hot, it was very dense, there was this very intense radiation field when galaxies were first forming stars. This epoch is extremely difficult to study because it's so far away and so long ago. But by using dwarf galaxies, we can try to connect the evolutionary history of a galaxy to what was happening in the universe So I'm going to show you a little bit of what that looks like. To do that, I'd like to use an analogy of studying a human population. And so in dwarf galaxies, we're using stellar populations to understand the history, and we're doing essentially like a celestial census bureau. But in a town, you might imagine taking everybody from, this is a small town in Oregon, you take everybody from the town and you set them out on Main Stoop and you take their picture. And from this picture, you could count how many babies are in this town, how many toddlers, teenagers, how many grown-ups, how many senior citizens, and then you could maybe back out the birth rate of people per decade. And maybe you do a little bit finer in the most recent times, right? Because you can tell a baby from a toddler from a preschooler. But you could have essentially the birth rate over the last 100 years or so of this town. Well, that's essentially what we do with galaxies. And so from Leo P, I'll measure the brightness and temperature of every single one of these little blue dots in here, every one of these stars. Just two properties, the brightness and the temperature of these stars. And when you plot up those two quantities, you get a graph that looks like this. So you have brightness versus temperature. And there's a lot of structure in this plot. And young stars hang out over here and old stars hang out over here. And so you can age date the stars in a galaxy by just measuring these two quantities. And so what I've done to show you, to demonstrate that, is I've simulated a galaxy on my computer, and I've created a galaxy that looks a little bit like Leo P, and I've color-coded now the stars according to their age. And so based on their brightness and temperature, all the young stars are in blue, and young being measured in billions of years, and the old stars are in red, and kind of the intermediate age stars are in the rainbow colors here. And so going back to our analogy of the little town in Oregon, you might have the millennials up here, these are the Gen Xers, and then here are the baby boomers. And that's you can do this qualitatively in a picture, but you can also quantify it. And so I can fit this with some sophisticated models, and I can come out with actually the history of the galaxy. And so this is showing the fraction of stars that were formed at a given age in the galaxy. So if we look back to the very, very early universe, in the first billion years, Leo P formed 20% of its stars. And then it looks like it got kind of quiet. And it didn't form any stars for 4 or 5 billion years. And then suddenly it started making stars again at a fairly constant rate. So while this is just really interesting to understand the history of an individual galaxy, we can also think about what was going on in the universe at that time. And if you think about the town in Oregon, and you think about doing the birth rate of a population, you might see that there's this baby boomer generation where you had this rise in birth around the late 1940s and 1950s. And so we know in our society that soldiers were coming home from war. It was post-World War II. There was economic prosperity, and there were a lot of babies being born. And you can think about the millennials even further, that these are the children of the baby boomers. And so the millennials show a significant increase in the population too. Well, this is the same sort of analysis we're doing. We're trying to connect what we see here with what was going on in the universe. And we think that what features we're seeing here in the early evolution of this galaxy is an imprint of the early universe. When you have this hot, dense, and intense radiation field, it hits all the galaxies in the universe. And this intense radiation field heats up the gas in a galaxy, and hot gas doesn't make stars. You need cold gas that condense in to make stars. And so one interpretation of this is that this hot, intense radiation field of the epoch of reionization stopped star formation in Leo P, and the galaxy got quiet for a few billion years. And until that gas could cool down and come back into the center of the galaxy, it wasn't able to do very much, and then it started making more stars. Okay, but in addition to that, you can think about how all of this star formation has shaped the galaxy. And we know that the universe started off with mostly hydrogen and helium. But inside of stars, it's like a furnace. And inside the very center of this furnace, there's nuclear fusion going on, and it's smashing this hydrogen and helium atoms to basically populate a significant part of the periodic table. So if we look at the periodic table, this is color-coded by what made the element. So in the very top here, hydrogen and helium were made in the Big Bang, but the different other elements were made either from, in small stars, the pink one, or the purple one was made in supernovae. The blue color is made from large stars, and these gray ones here are made by people in a lab. Let's focus on oxygen. We know oxygen are made in large stars. And so if we know how many stars from the analysis I just showed you, if we know how many stars were formed over the history of the galaxy, then we know how many oxygen atoms were also formed in the galaxy. And so we can do this accounting exercise that if we know how many galaxies were formed, how many oxygen atoms were ever made, then we can also start counting up the amount of oxygen atoms that are still in the living stars and that are in the gas. And we can compare these two numbers. So oxygen ever made versus what's still in the galaxy today. And if we had a closed system, these numbers would be equal. You know, if you think about our little town in Oregon, if nobody moved in and out of the town, you know, it would be a closed system. But people move in and out, and so the picture of our town may not really represent the birth rate of the town. It represents, you know, inflow and outflow and birth rate in the town. But by doing this, you know, we were able to measure that Leo P has only got 5% of the oxygen atoms it ever made in stars. Essentially, 95% of the oxygen atoms are missing. So the interpretation of that is that the galaxy got rid of them. The galaxy has created a galactic wind that has spewed these oxygen atoms out of the galaxy into the intergalactic median, or maybe even just into the halo of the galaxy. And here's a picture. The galaxy winds happen, but they're really, really hard to measure. And here's one recent image of a spiral galaxy with a galactic wind detected here in this purple. Really hard to measure, really hard to detect. But the measurement of these from these stars in Leo P, we've been able to determine that through a galactic wind process like this, this little tiny galaxy has kind of expelled the majority of oxygen atoms that it's ever formed. Thank you so much.
All right. Thank you, Galactic Goddess. All right, we have questions right up front. We'll start with you.
Between the really large galaxies like M103 and the small ones. In other words, why is this galaxy so massive and why is this a dwarf galaxy? Why is this so small?
So the question was, why is Leo P so small compared to some of these other galaxies? And this is still an open question of research, but one of the ways we think galaxies are made is that they start really small. So galaxies start small, they merge together, and they can form and build up bigger and bigger galaxies. And we also understand now that that's not the entire picture. We know that dwarf galaxies do merge and help build up mass in larger galaxies. But if you take something like that and think of it as like a seed of a massive galaxy, you can also build up mass by just having additional gas flow into the galaxy, this cold gas accretion, and you've got material accreting and bigger and making it bigger and bigger and bigger. So it's just sort of the diversity of how galaxies are formed. But we think that the smallest, that the basic building blocks of galaxies start really small.
All right, you, sir, in the back with the glasses.
What is the dark matter distribution of dwarf galaxies compared to larger galaxies?
Okay, the question was, what is the distribution of dark matter in small galaxies versus large galaxies? And I almost want to give this question to Brandon because
it's your stage.
He does. This is the work he does. But dwarf galaxies are what we consider dark matter dominated, and so they actually have a larger amount of dark matter per number of stars and gas particles than the more massive galaxies do. Great question. Great question.
It's possibly related to how star formation forms in these, and how stars can shut down star formation in a galaxy by feedback. And so in these smaller galaxies, you have a lower gravitational potential, and so it's easier to blow out all the gas and maybe shut down stars. That's one possible explanation.
Hey, you're stealing my show here.
I know. I couldn't help it. Or maybe it's maybe warm dark matter. Maybe there's something different about
maybe there's warm dark matter. Yeah.
Other questions?
So, okay.
No, go ahead. Go ahead. No,
let's go. Let's go.
Oh,
I'm
okay.
good.
All right. Okay, go ahead.
Yep.
And from your side, on the right-hand side, there's a little groove there inside that. What is that?
That's called the red clump. Great eye. That's a really small feature. It's called the red clump, and it extends into what's called the horizontal branch. And so for those of you familiar with this type of diagram, the stars are, the young stars are in one part, and the old stars are in another part of the diagram. And so you can imagine as the star ages, it changes position in this diagram. So the stars are kind of moving, right? If you were to take a snapshot over time, you'd see a star kind of changing in brightness and temperature. And there's this one feature where stars kind of clump down in the red clump into the horizontal branch. And this is when the stars have started fusing helium. A lower mass stars started fusing helium in their core rather than hydrogen in the core. And it changes the temperature and the brightness.
All right, one more question in the back.
I'm sorry? So the galactic wind, if you have a whole bunch of stars that are exploding in some small region in space inside of a galaxy, the combined energy of these supernovae will kind of push the gas surrounding gas and push it and push it and push it until finally it breaks through the galactic disk, and it will just spew this like really hot gas outside of a galaxy. And it doesn't usually happen all around the galaxy. It's usually fairly focused in one region because it takes a lot of energy to kind of clear a path out and be able to release that. So it's this release of energy and material from a galaxy into its environs. And it could be into the halo of a galaxy, which may still be gravitationally bound and the material may rain back down in through gravity. Or it can be, if it's moving fast enough, like above escape velocity, it will leave the galaxy and be, basically we call it polluting the intergalactic medium.
All right.
Galactic pollution.
With that, let's thank Galactic Goddess one more time. If you have more questions, find her afterwards and ask her.